Have you ever just looked at something and seen a pattern, and you just had to wonder, what's the secret rule that's making it work? From the way a flower's petals are arranged to how your savings account grows, our world is just full of these predictable patterns. Well, today, we're going to unlock the code behind them. We're diving into the amazing world of sequences.
So here's what we're going to cover. First, we'll tackle the big one. What even is a sequence? Then we'll get into the two major types, the nice, steady growth of arithmetic sequences, and then the explosive growth of geometric ones. After that, we'll look at how to find the middle ground. And finally, we'll see where all these powerful ideas pop up in the real world.
All right, let's get right into it. Part 1. What in the world are we talking about when we say sequence? Honestly, just think of it as the secret language that patterns use to communicate their rules to us.
Let's just try one. Take a look at this first line of numbers. 2, 5, 8, 11. What's next? You probably see it, right? We're just adding 3 each time. Okay, how about the second one? 3, 6, 12, 24. Here, the rule changes. We're multiplying by 2. And this last one? 1, 4, 9, 16. Yeah, those are just the square numbers. See? Our brains are literally built to spot these kinds of rules.
And that, my friends, is all a sequence really is. It's just an ordered list of numbers. And each one of those numbers, like the 2 or the 5 we just saw, gets a special name. We call it a term. The key word here is ordered. The order is everything, because that's what reveals the pattern.
Okay, so let's zoom in on that first type of pattern we saw, the one that's all about addition. These are called arithmetic sequences, and a great way to think about them is like taking steady, consistent steps forward, one after another. So, here's the official deal. An arithmetic sequence is any list of numbers where you are always adding or subtracting the exact same amount to get from one term to the next. The word you've got to remember is constant. It's predictable. It's steady. There are no surprises here, just consistent, reliable change. And that constant value, it has a name. It's called the common difference, and we usually just shorten it to the letter D. This little number is the secret code for the entire sequence. Seriously, once you know the first term and you know D, you can figure out any other term in that sequence, no matter how far down the line it is.
This simple example makes it so obvious. Imagine you start with $5 and you decide to save another $5 every single week. So week 1, you've got $5. Week 2, you add 5, you're at 10. Week 3, add another 5, you're up to 15. That common difference, our D, is just 5. It's that simple, steady growth in action.
Okay, your turn. Have a look at this sequence. 7, 11, 15, 19. What's the common difference? What are we adding each time? Yeah, it's 4. So the next term has to be 23. Simple as that. You just cracked an arithmetic sequence. Now hold on. If arithmetic sequences are just steady little steps, then geometric sequences, well, they're like taking giant, powerful leaps. This is where things get really exciting, because we're not just adding anymore, we're multiplying.
The definition looks kinda similar, but trust me, the operation is way more powerful. In a geometric sequence, you get each new term by multiplying the last one by a fixed number. And this creates a pattern of growth that just, it accelerates like crazy.
And that fixed multiplier, we call that the common ratio, or just R. This little number is the engine of the whole sequence. If R is bigger than 1, you get that explosive growth. But what's interesting is if R is between 0 and 1, you actually get the opposite, decay, where things shrink over time. A viral video is the perfect way to picture this. So, day 1, your post gets 100 views. Not bad. But then it doubles every single day. That doubling, that's our common ratio, R equals 2. Now look how fast these numbers climb. 100, then 200, then 400, then 800. By day 10, you know how many views that would be? Over 50,000. That is the power of geometric growth.
So we've got these two big ideas for sequences, right? One based on adding, the other on multiplying. So a natural question is, how do you find the perfect middle number between two other numbers inside each of those systems? Okay, so you absolutely already know the arithmetic mean, you just probably call it the average. It's that simple. You just add two numbers up and divide by 2. So for 4 and 16, you add them, you get 20, divide by 2, and you get 10. And notice 4, 10, and 16, that's a perfect little arithmetic sequence with a common difference of 6.
Now, the geometric mean does the exact same job, but it does it from multiplication. To find it, you multiply the two numbers together, and then you just take the square root. So for our same numbers, 4 and 16, we multiply them to get 64, and the square root of 64 is 8. And check it out, the numbers 4, 8, and 16. That's a perfect geometric sequence where you're multiplying by 2 each time. It just works.
So here is the big takeaway, the thing you have to remember. It's about using different tools for different jobs. If your data is linear, meaning it changes by steady amounts, like trying to find your average test score, you use the arithmetic mean. But if your data is exponential, growing by percentages, like, say, your investment returns, the geometric mean is going to give you a much more realistic picture of what's actually happening.
Phew. Okay, we have covered a lot of ground, right? From steady steps to giant leaps. But what's the point? Why does any of this matter? Well, let's bring it all home and see where these patterns are hiding all around us in plain sight.
You know that compound interest your bank talks about? Yeah, that's a geometric sequence. Biologists modeling how a population grows? Also a geometric sequence. The value of a brand new car going down each year? That's a sequence too. Even something as beautiful as the spiral in a nautilus shell, it follows these exact mathematical rules. So these aren't just abstract ideas for a class. They're the basic building blocks of how things grow, shrink, and change all around us.
So today, we unlocked the basic codes for sequences built on simple addition and multiplication. But really, this is just scratching the surface. It leaves us with an even bigger question. What other rules can a pattern follow? What happens when a new term depends not just on the one before it, but maybe the two before it, like in the famous Fibonacci sequence? The world of patterns is just massive, and now you've got the keys to start exploring it.